Bismillah ar-Rahman ar-Rahim. Today we are going to speak about the reduction of order. This is a technique to find the solution set or the general solution of second order linear differential equation. And the idea behind this one that we will be given one of the solution, because since we are speaking about the second order differential equation, it means that we are going to have two solutions, and these are linear solutions. One of them will be given, and we need to find the second solution for the differential equation. So we are assuming that the y1, which is the solution of equation, is given y1, the non-trivial solution of the equation 1, which is defined on an interval I. And we need to find a second solution y2. This is the idea for the reduction of order. Second order differential equation, it means that we must have two solutions, y1 and y2. We will be given one of the solutions, which is y1, and we need to find the second solution, y sub 2. So that the set consists of y1 and y2. This is the main part, which are linearly independent on the given interval I. And since they are linearly independent, it means that the quotient for y2 divided by y1 is non-constant on I. This is the meaning of the non, or of the linearly independent solution. The quotient for the two solutions is non-constant. Or it can be written as y2 divided by 1 equal to yx, or y2 equal to a function of x, ux multiplied by y sub 1. So we need to find the second solution from this relation. I need to find u. So to find this, we need to substitute y2 by ux multiplied by y1 over the given solution. And this method is called the reduction of order. Why? Because of this method, we are going to solve a linear first order differential equation. So we are going to reduce the order from the second order to first order differential equation. To speak about this generally, so with that we have this equation in the standard form: y sub 2 plus b of x y prime plus q of x y equal to 0. Given that b of x and q of x are continuous on the interval I. So if we replace the y2 by the relation y equal to y, or ux multiplied by y1, then differentiate, find the first derivative using the product rule. It will be uy prime plus y1 u prime. Second derivative will be uy1. Second derivative plus 2 y1 prime u prime plus y1 u second prime, or second derivative. Now if we substitute this relation in the given equation, this is y1 and this is y2, we'll have this equation, which is u multiplied by, just combine the similar terms, y1 prime plus b y1 prime plus qy1, which is equal to 0, because this is the original function, or sorry, the original equation. So this part will be equal to 0. So we will end up with y1 u double prime plus 2 y1 prime plus b y1 u prime. Now this is second order differential equation, and we need to reduce it to first order. So if we replace or substitute y u prime equal to w, so the equation will be converted to a first order differential equation. Using this substitution, w equal to u prime, then the second derivative, or the the value prime will be u second derivative. But that will give me the first order. And u prime will be replaced by the value which is equal to 0, which is homogeneous equation now. Now put it in the standard form, we will have dy over y plus 2 y1 prime y1 or divided by y1 dx plus b dx equal to 0. This equation is separable equation. I can integrate the value over the value plus integration of 2 y1 prime divided by y1 plus b dx equal to 0. This is equal to ln of the value. This one is equal to plus ln of y1 square plus integration of b dx. So it can be written in this form. So it is ln because we have ln plus another ln. We can combine them together in one single logarithm. That will be ln of the value multiplied by y1 to power 2 equal to minus integration of b dx plus constant. See. Convert it to exponential and then find the value that will give me. This is the value which is equal to y u prime equal to c1 divided by e to power integration b of x or dx divided by y1. Now if we integrate, I will have y equal to c integration of all of these divided by y1 square, which is this formula. So the second solution now can be written as y2 equal to y1x multiplied by the integration of e to power minus b of x dx divided by y1 square. So we are going to apply this formula to find the second solution. So the second solution, y sub 2 equal to y1x multiplied by the integration of e to power minus integration of b of x dx divided by y1 square dx. Let's apply this idea for some examples. The given problem, we need to find the second solution, given that y1 is a solution of the given differential equation. So use the reduction of order formula to find a second solution y2 sub x. So we are given one of the solutions, which is y1. And we need to find the second solution. We know that y2 of x equal to y1 of x multiplied by the integration of e to power minus integration of b of x dx divided by y1 square. This is the formula of the second solution. b of x from this equation, 1 by 1, is equal to minus 4. So the integration, or minus b of x dx, that will be integration of 4 dx, which is equal to 4. So we are going to have now y2 equal to y1, which is e to power 2x multiplied by e to power 4. This is 4x. This is 4 is 4x. Of 4x divided by y1 square, which is e to power 2x all to power 2 dx. Which is equal to e to power 2x integration of e to power 4x and e to power 4x will cancel each other. So we'll have only dx, which is equal to e to power 2x multiplied by x. We can say also plus constant. But since I don't need the constant, if we go back to see the formula for the second derivative, see this one only, the constant will be left later on. So there is no constant. I will just write it as x. So the second solution is equal to x e to power 2x. So you can say now the general solution for the given differential equation is written as y equal to c1 y1 of x plus c2 y2 of x. This is equal to c1 e to power 2x plus c2 x e to power 2x. So this is the general solution for the given differential equation. Have another one example. For that we have y double prime plus 6y equal to 0, and we are given that y1 equal to cosine of 4x. So b of x for this equation is equal to 0. Because the general solution is y, or the standard form it is y double prime plus b of x y prime plus q of x equal to 0. So b of x is the coefficient of the y prime. And I don't have y prime in this equation, so b of x equal to 0, which means integration of b of x is just constant. It's a constant c. So the second solution, which is y2 equal to y1 integration of e to power minus c divided by y1 square dx. This is equal to y1 equal to cosine 4x multiplied by the integration of e to power minus c divided by cosine 4x all to power 2 dx. Or it is cosine 4x e to power minus cos c 1 over secant square. Oh, it is that's 1 over secant square dx, which is equal to cosine 4x e to power minus c multiplied by integration of the secant square is equal to tangent. But we know that cosine and if we multiply by the tangent, I will have only sine because tangent is sine over cosine. This will be cancelled with the, because we know that tangent is sine for x over cosine 4x, so this will cancel this one. So we'll have equal to e to power minus c multiplied by sine 4x. And I can take all of this is only a constant. So we can take y2 of x equal to sine 4x. And the general solution, which is equal to y equal to c1 y1 plus c2 y2, that is will be c1 cosine 4x plus c2 sine 4x. So this how to find the second solution of the given differential equation using the reduction of order.